So today we are going to be trying to derive the special theory of relativity, and really what we're going to be showing are the Lorentz transformations. And I want to do it without you having any prior knowledge about world lines or any of the other tools that are sometimes used to teach this subject. So we're going to be deriving this really with just one very simple axiom. Well, first of all, the special theory of relativity deals with objects moving at constant speeds. So in other words, we're looking at acceleration equals 0, okay? And then the speed of light is constant, and here's the kicker for all observers. And this is really what Einstein was thinking about when he first started to put this together. So a little bit of history. The Lorentz transformations, I think, were known about in about the middle of the 19th century, but they were just sort of a coordinate transformation that Lorentz observed for objects moving at a constant speed. Einstein put all this together and put it under the umbrella of looking at light and doing thought experiments with light. So without further ado, let's jump in and look at what the thought experiment is. So imagine, this is pretty typical in my videos, but imagine you have a box, okay? And the box is traveling at some speed v, and there is also a coordinate system back here where this is, let's try that again, where this is y and x. So the box is traveling in the positive x direction, and there's going to be a light particle in here, or a photon you might call it. And in this first, we can call this t0, and this first time this light particle is at this point. So the way I want to draw this is I want to do a series of jumps, okay? So we're going to have these sort of dividing lines, and we're going to draw different time frames. This might be t0, this will be t1, and then we're going to draw t2 over here. And the simple thought experiment is this object v, or this object that's traveling at v, what happens when the photon reaches this other end? So we're still going at v here, but now the photon is over here. So this guy would have been pointing this way with c, and now it's here, and it's sort of bounced off the edge and it's pointing back with c. And then finally over here, it's at a further position, and then the photon is back at the beginning again. So, and this thing is still moving at v. We want to look at these interactions. Now, we've already said the speed of light is constant for all observers. So what I want to sort of define here is we'll call this a maybe delta TA that takes us from T0 to T1, and then a delta TB that takes us from T1 to T2. So you would think that these quantities will be equal, right? Because obviously for someone inside here, if you're an observer inside this thing, you're going to see this photon flash back and forth in the exact same time interval. Okay, so let's do a little bit of algebra. If we think that the photon, let's draw a reference frame. This would have been, say, the first place we were at. So this coincides with this point. And what we should notice is that this path here is c delta TA. This is how far that photon traveled, okay? And this is obviously the length of the container. And then this distance here is v delta TA. So we can construct a simple equation here that we use delta TA in. So what we're going to get is we're going to get, it's going to be v delta TA plus L equals c delta TA. So rearrange, let's rearrange for delta TA, and you will get, make sure I do this right, so it'll be v minus c. I guess I'm doing this strangely. Let's bring that over there. L equals delta TA C minus V. Then we can say delta TA equals L over C minus V. Okay, so this is one equation for delta TA. Let's use orange to use another one. So on the way back, the photon obviously, so here's a bit of a bizarre thing. We're going to draw this orange line here. Okay, sorry, this is not drawn super well. This orange line here is actually going to correspond to some distance here, which we started at. So it's almost like the path that the photon traveled is now somehow compressed, where this is C delta TB, okay? And then this little bit right here is V delta TB. And then, of course, the whole thing is L. So you might be surmising what's going on here already, but then we're going to get L equals C delta TB plus V delta TB, and then rearranging, you get delta TB equals L over C plus V. Okay, so I should have done this in orange, but that's okay. So what we see is that it kind of looks like these two quantities are not equal. And I'm going to write this with an asterisk, but is TA not equal to TB? Now the answer is they are equal. This time slice has to be equal. We know this from our first postulate. But it's confusing, right? Because if you think L is a constant and C is a constant and V is a constant, how can this be true? Well, it turns out the answer that we see much later is that it's actually the length that contracts, and we will show that, and that's how this thing is actually true.